Hello. In this video clip, I will introduce a testing and verification series of TOP-SE. I am Tanabe Yoshinori from Tsurumi University, a lecturer of TOP-SE. You see the list of lecturers teaching this course series. Almost all of them are practitioners or have a previous industry experience. And this reflects that the series not only teaches technologies themselves, but also focuses on how to leverage them in the business. The goal of this series is to acquire knowledge and skills in techniques for software quality, such as testing, static or dynamic analysis of programs, and that includes model checking. The courses in the series are divided into three groups, though the first two have only one course each. The theme of the first group is testing. It has one course called Introduction to Testing. I guess you, as an engineer, perform testing as a daily task. You may be familiar with various testing techniques, such as orthogonal array testing, or testing concepts such as black box testing, white box testing, test coverage, and so on. In this course, we review testing from the standpoint of software engineering. We not only cover techniques and concepts I have just mentioned, but also discuss the positioning of testing in the software development process. The second group is about static analysis, which also consists of one course called program analysis. This course will be taught in an omnibus format by 4 instructors. They are researchers interested in program analysis, working in academia and industry. The term static analysis has been widely accepted in the engineering community by now, so you have perhaps heard this term, and some of you may even use static analysis tools in daily tasks. But unlike the previously explained course of testing, this course program analysis handles fairly advanced topics listed in the slide. Testing is a technique to confirming that a program works correctly by running the code. On the other hand, static analysis is the practice of verifying code without executing the code. Thus, you can get results that do not depend on examples of data which you choose it. The third group is about model checking, and it has 6 courses. Before talking about each course, let me explain the model checking technique itself. In model checking, you construct a mathematical structure called a state transition system. And that represents all possible states of the system you want to verify, and verify that is correct or is safe or is robust or confirms the specs or whatsoever. Known model checking algorithms efficiently search the transition system and determines whether there is a path that causes a problem. But maybe that's too abstract. Let me give you an example. The figure in the right is a schematic representation of a transition system. Consider that the green cell represents the starting status of a system. And this system opens a file and closes file. At the cell shown in yellow, the system opens a file and it closes in the cells shown in red. And the question is, are all open files will they eventually be closed or not? What do you think? In this particular system, that is not the case. In fact, there is a path. Now you see, so if you follow this path, a file is opened once, and immediately after that it is closed, but it is reopened, and after that it will never be closed. Because the transition system shown here is very small, so it may not be difficult even for human to find such a counterexample. But for a real system, the number of states is huge. It has often millions of states, sometimes billions. In such cases, it is usually difficult for a human to find all such problems in the system. Model checkers with sophisticated algorithms implemented explore such transition systems exhaustively and effectively to find this type of problems. Here is a typical approach for detecting problems using model checking technique. Once specifications are fixed, you build a state transition system based on the specifications. And you list expected properties that the system should have. Then a model checker explores the transition system against the expected properties. And if it concludes that there is no problem, then it reports OK, or if not, it reports counterexamples. It may sound simple, but when you actually try to approach this technique to your system, you may find a lot of issues to be solved. For example, you may wonder how to write transition systems, or you may want to know how expected properties are expressed for the model checker to understand, and so on and on and on and on and on. Okay. 6 courses of model checking in TOP-SE are designed that the students can get answers to such questions. And as a result, he can effectively utilize this technique in his development tasks. So here are overviews of model checking courses. And the first course, Introduction to Model Checking, which consists of 2 parts. Students learn fairly basic facts and concepts, such as what transition system is or how to write expected properties. And then the second one, Design Model Checking, focuses on how to effectively use the technology in software development processes. And third one, performance model checking, and the concept of time is discussed. And the next one, design verification of concurrent systems, a mathematical model called CSP will be discussed. And the last one, model checking case studies, go through some typical cases. Okay, so what is the significance of learning model checking technologies? One is obvious and very practical. You can gain means to track down how to reproduce problems in a system. And such problems are typically caused by parallel execution and often very hard to find. But there is another reason. In TOP-SE, we emphasize the importance of capability of modeling. Through learning this technology, you can acquire the ability to do modeling and to abstraction. So let me summarize. Testing and verification series consists of 3 groups of courses. And through learning these courses, the students can acquire knowledge and skills in techniques for software quality. Thank you very much for listening.